modeling an ongoing epidemic, which is something different from, so there's a big difference, say, if you do epidemiological studies and with modeling for something that has, I mean, that was in the past. For instance, you could be interested in, say, dengue epidemics and the relation to climate. So you need a long time series of climate variables, of dengue cases, and then you need a method to correlate or whatever kind of method you use. But these are things that the data is available. You don't need the data of yesterday. You have the data from last year, and that's okay. That's fine. When you have an ongoing epidemic like COVID-19, you don't have the data if consolidated, let's say. You don't know how many cases there are today, yesterday, last week. This is still being counted and so on. So you need different methods. And which also restricts what you can actually do in terms of modeling and data analysis for ongoing epidemics. So this, this lecture is based on the experience of our group on COVID-19. I will be talking about essentially about COVID-19 in Brazil. But let's say this is kind of example of the situations that happen. And just to, if you are interested, everything we have done can be, not everything, but with part of our work can be found in this website. So when in March 2020, when there was the actual start of the epidemic here in Brazil, instead of running for data and publishing papers, we went more for a kind of public service. We have a website with analysis, which is this website, and also to interact and with the government of the state and the city of São Paulo. So here, if you are interested, it's in Portuguese, obviously, because it was meant to be something really local. Okay? So let me now go to my presentation here. Okay, so that's the epidemic curve of severe cases of COVID-19 in the state of São Paulo. Okay? So until February 2023. Okay, is this working? Yeah. Okay, so I will come back to this curve. First, okay, forget about simple models that you see in the textbooks, okay? Probably you have never seen anything like that in a textbook, where they have a lot of different waves, peaks, and ups and downs, and so on. Now we know the explanation for most of these things. It's connected to the new variants, and also to the fact that immunity may wane. It's not permanent, and so on. But anyhow, so this is for the city of São Paulo, and here, just for you to pay attention, that this is made week by week. So we use weekly data, and here there's a part which is in red, and I will explain you why there's a part in red in some minutes. Okay, so, and this is the number of people that got hospitalized per week in the state of São Paulo. So why I'm showing you the hospitalized cases. So hospitalized cases, because, sorry, when a person gets admitted at a hospital with suspect of being having COVID-19, this generates a notification. Right? So it takes some time for the notification to be actually generated and so on, but this has to be, there's a notification. There's a record. If the person just goes to the doctor and it's a mild case, and the doctor say, okay, go home and so on, it's not mandatory to have the notification, so you don't know actually the number of cases of mild cases. It depends on the policies of each municipality, which are pretty much different from one place to the other. So a good way of looking at the COVID-19 epidemic in Brazil is looking to the hospitalized cases, which is a proxy to the number of total cases. Okay? So, okay, so what was the situation when at the beginning of the epidemic? The beginning of the epidemic, what did we know and what did we use? So there were modeling initiatives like using compartmental models, agent-based models, stochastic models, and so on. There are many groups working on this. And what people did initially were essentially calculations of RNOF. Lots of people doing this. And for the case here in Brazil, the most sensible thing to do is calculate RNOF per municipalities or per cities or per metropolitan regions, and not for all Brazil, which doesn't make much sense. And one important thing about this calculation of RNOF, and sometimes at the very beginning, instead of calculating RNOF, you could also just calculate the doubling time of the number of cases. Okay, you have the certain number of cases reported, you look for the doubling time. What was the use of this? There was a use that was actually interesting, which is the doubling time of at the very beginning of the epidemic. I'm talking March 2020, was pretty much similar, for instance, to what has been the doubling time in Italy or in Spain. And everybody knew here which kind of disaster you had in Italy at some weeks before. So we had the same parameters here. So meaning that we could use the fact that what happened in other places as a kind of alarm, okay? To say, okay, we have the same parameters. We're at the very beginning of the epidemic. We have the same parameters, say, as Italy. And, you know, Italy was a catastrophic situation. We can take action here earlier in order to avoid such a catastrophic situation, which, depending on the state, worked because decisions were taken by states and by municipalities. Okay, so that's one point, that calculating parameters at the very beginning of the epidemic and comparing to things that had happened in other places may be very useful for decision making. Yeah. So also in 2020 we had a lot of scenarios. So you use modeling with mechanistic or stochastic models with with the compartmentals and so on. And in order to estimate the impact of non-pharmaceutical interventions. One thing that that is important to notice at that point was at the very beginning of an epidemic like that, your models are not meant to be predictive in the for more than 2 or 3 weeks. Okay, so there was a lot of interest in people saying, can you make a model and predict me when the epidemic will be over? So that's a typical thing that decision makers would ask you, or journalists also want to know this, or when is the peak, and so on. And I think that a lesson for people that do the modeling was, okay, you should pay attention to what you say. And what happened actually is that models could not predict anything like the epidemic curve that I just showed you some minutes ago. So the models would be much more were much more useful to compare scenarios, like if I do introduce a non-pharmaceutical interventions, what's the proportion of cases that you expect to avoid, and what will happen if I close schools, or what will happen if I have normal classes in schools, and this kind of thing, always with the sense of being a possible scenario, not a predictive situation. So, okay. So back then, and at the beginning of the epidemic, we had no knowledge of vaccine efficiencies because there were no vaccines. Very few knowledge of behavioral effects. Behavioral effects is like, well, it's the subject of the school, but at that time it was not obvious that, for instance, if would people actually agree to obey, and for how long, for the non-pharmaceutical interventions, for instance, using masks, for instance. It's still under discussion of how useful masks are, because everyone knows that masks work. I mean, if you do a good mask, N95 mask and so on, they work. But do mask mandates work, which is a different question. And until today, there's a lot of discussion of will people actually follow what the government or the local authorities are saying to do or not. Okay? So, and obviously at the beginning of the epidemic, we had no idea that there were so many possible variants, and that the immunity would wane and so on. So with all of this, an example of important work, which was already mentioned in the first lecture of Joshua, is the estimate by the Imperial College group that if no action is taken, you could have 2 million deaths related to COVID-19 in US, and something like 500,000 in UK. And that generated a lot of discussion, because obviously there is no such thing as no action is taken. Okay? So there's always a reaction, even if the government of the country, of the city, of the state doesn't enforce rules. People will react somehow, will take action by themselves. Okay, so this scenario of the 2 million would be in US would be in kind of worst case scenario. At the time this appeared in the newspapers, this was not very well communicated actually, and this has some importance, as later on people started to say that, well, people that do the modeling actually try to drive people to the panic situation and so on and so on. But actually, the calculation was actually, the models are pretty much okay in the sense that if you take into account that this is the worst case scenario, which didn't happen. So now, if you look into present day situation, so we know much more. Okay? We know about vaccines. We know their efficacies, and you can include vaccination in the most models. So now we know that immunity, you have a waning immunity situation with COVID-19, that the immunity kind of decays, if you want. And this is important to explain long-term trends in the epidemic. We also...
Como estamos? Ahora.
Hello? What's happening? Okay, let me see. Okay, I think so, yeah? Okay. Yeah. Okay, so let's go. What we also learned during these years is that so long-term predictions have essentially failed. And another thing is that quantification of uncertainties is very important. It's important for the models, and to make sense. And it's also important to communicate uncertainty, which is a challenge for scientists and for science people that communicate about science to the larger public, which is the fact that when you do models and you use data to fit your models or make any kind of prediction or any kind of calculation, you have uncertainties, and you have to treat these uncertainties with statistical methods, which can be done. Yeah? And but you also should be clear when you communicate these uncertainties to a larger public, because that's difficult for people to apprehend, actually. So it is a problem. And what we have seen many situations in, not only in Brazil, but worldwide, of people communicating results about that data analysis or modeling in general, and in a way that kind of made people think that there were certainties about it, that the prediction is this and that. Okay? The next peak will be on November 14 at noon. Okay? So and this this was really a problem with many scientists doing this kind of communication in a way that gave the impression that we know much more than we actually do. Okay? So, okay, this is just for you to remember what the models are. This is a simple SIR model. You have seen this many times here. But so the first thing for us to remember is, so simple models like the SIR or SEIR or some variant of that, what are they good for? Okay? So in a situation where you have still a lot of uncertainty and an ongoing epidemic, so they give you maybe a general view of what can happen or the possibilities. They allow you to understand more or less what R0 is, and there is this relation between R0 and the final size of an epidemic, which is model dependent, but, well, gives you at least an idea of the order of magnitude of what the kind of problem you have. So for this, simple concepts like R0 and the total size of epidemic are useful, but they are say, just to give you an idea of what kind of situation you have. Most of the time, these simple models won't produce anything but this kind of general order of magnitude ideas. They will not be useful to generate predictions or to guide policymakers and so on, so on. You need much more complicated models. Okay? What kind of model would be a more realistic model for COVID-19? Right? So, okay, let me ask you, what compartments do you think are important to have in a compartmental model for COVID-19? You have susceptibles, infected, and infected, infective, and recovered, but what other compartments would be interesting for a model? Hospitalized people, yes. So you would have infected people, which could be, okay, infective, and then they could be mild cases, which stay at home, and hospitalized people that go to the hospital, and they would have different parameters. For instance, number of contacts of people that are hospitalized is different from the number of contacts that people that are not hospitalized. And also the fatality rate would be much higher for hospitalized people than for non-hospitalized people. Other ideas. So, to include variants depends what you mean, but of this, if you know that there's a new variant, then okay, then it's you just write a model with two variants, which is you have people that are infected with variant A and people are infected with variant B, and so you have different parameters, and then you can have cross immunity or no cross immunity, depends. But include variants before they happen. We don't have any, because it's an evolutionary process which is beyond the realm of this kind of models. So, but what else? What else? More compartments. Only hospitalized? Asymptomatic, yeah. So you could then divide the infectives in asymptomatic, symptomatic but mild, and symptomatic going to hospital. More. Death. Yeah, diseased people, obviously. Okay? Why is diseased people important, and why is hospitalized people important? Because these are data that you have. You get the data about hospitalization and about death. You don't know how many people got the sick today, because you cannot survey the population as a whole, but these are the kinds of things that you know. More compartments could be interesting. Exposed, so there are people that are exposed and are not yet infective, and you can introduce a pre-symptomatic, which is people that are infective, but they have no idea they are, and yeah. Okay, so if you have vaccines, then you have the vaccinated population and non-vaccinated population. You can also divide your population with respect to status of vaccination. More. So quarantine people, yeah, you can have a compartment for quarantine. Reinfected, yeah. Reinfected, I mean, reinfected are infective, but sometimes they are a person that is reinfected maybe has different parameters. Could be a new variant, or could be just reinfection by the same variant also. Incubation period, which is the pre-infective thing. Okay, yeah, you can include, that's an effect, it's not a new compartment, but it's a kind of time variable with less immunity. Yeah, could do this, yeah. And, well, there's one thing nobody said, but which is very important. It says age. Okay, age, because death rates, recovery rates, I mean, all rates you can think about depend on age. So you have to divide each class in class ages. You can, yeah, this corresponds in general, for more general cases than COVID, to risk exposure, yeah. Well, I guess that there is somebody modeling, because there's a lot of modelers in the world. But the point is, you could ask yourself, what classes should I actually include in a model? Okay, because you see there are lots of them. For instance, we had a model which was developed with a kind of consortium of modelers based in Oxford, where we had people that are hospitalized, but you had people that need hospitalization and get the hospital, and people that need hospitalization but don't get the hospital. And then people that are in hospital that need ventilators, and the people that don't need, and then you have also the people that need but don't get. So you can find, okay? So you say, okay, so, but what are finally the compartments I should include? So if you're doing something where you try to do something realistic connected to the data, first thing is, what are your data? If you have data for instance, diseased people, you need a disease class. Okay? And also, there's a point that what are the parameters that you know? Because, you know, increasing a model is easy, but you have the hell of parameters. You don't know the parameters. And if you have too many parameters, you fit anything. Okay? It's called over-parameterization of a model. So you want to be reasonable about the parameters. So if you don't have, for instance, any idea, if you're doing a theoretical model, and for instance, you have no idea, you don't have data about number of beds, so number of ventilators, okay? So it's limited, but are we close or not to the limit? If you don't have any idea, then it's a parameter that will be around in your model, which have no way to know, okay? So you should be, it's a kind of art of modeling. You should be reasonable about what you put or not into a model. Okay? So, okay. And then you have all this age structure thing. So how many age classes should you have in a model? That's also a question. Okay? So, so it will depend on the kind of question you're asking. What do you want to calculate with your model? If you are doing something which should be really realistic for policymakers, probably you will divide your population in age classes of 5 or 10 years, which will give you 10 to 20 age classes. And this means that you have to know also the contact rates between people from age class 1 with age class, I don't know, 5. So you have to have contact rates between the classes and so on. So lots of things. But sometimes you don't need all these things. And I will show you some works we have done where we have only 3 age classes. People that are the young people, teenagers and children, adults, and then people over 60, for instance, because we know that there are differences between these categories and so on. But sometimes we don't know the difference between 40 and 50, but we know that over 60, so you have larger things. Okay? Well, so, sorry, that's not a good slide. I will show you some examples of things we have done which illustrate what can be done when you are in this situation. You have an ongoing epidemic. So there's this parameter RT, which is the number of secondary cases generated by a primary case of COVID. Okay, so this depends on time, obviously, but at time 0, at the beginning, it is just R naught. Then you have other as your number of susceptibles becomes depleted, decreases, then the effective reproductive number decreases. And the point is that you can calculate RT without writing a compartmental model. So it's a little bit more mathematical. I won't do the demonstration. If somebody is interested at the end, you can talk to me. It's just you have what people call a renewal equation, which just says that the number of the incidents today is the incidents some days ago times the parameter, which will turn out to be the generation time. Okay? And knowing the generation time distribution and the incidence, you can calculate R. Okay? You don't need a model. Okay? Do we know the generation interval? So I think Joshua has talked about this previously. And so we actually don't know the generation interval. And generation interval, well, if you don't remember, it's if I get infected today, when when will I infect the next person, okay? And so this interval is the generation time interval, and you have a distribution. You don't know, because for a respiratory disease like COVID-19, you don't know when you got infected. Maybe you have an idea, and you also don't know whom you infected, actually. Because you try not to infect, but you don't know. So what you know better is the time of onset of symptoms, and then you use what is the serial time distribution, which is the same concept, but instead of talking about the moment you got infected, it's the time when you got the first symptoms, and the person that you infected got the first symptoms. So you have and this is better documented. So they have works that estimate the serial time distribution. Right? So with this, you can calculate R of t. Here in this formula, I is not the usual I. I is incidence, number of cases, new cases per unit time. It's not the active number of cases. So, but now comes the point which makes your life a little bit more difficult, is you have to know better about your data. You probably don't know, if you go back, oops, you just know that you need the incidence, okay? Now, this is the number of new cases per day or per week, but you don't have this number. Why? Because, well, first, there are lots of cases that are asymptomatic and cases that are just not reported. People don't go to them. If it's a mild case, people don't go to the doctor. And if they go to the doctor, maybe the doctor will not report this case, because I mean, he's overwhelmed by lots of people, by lots of people that are ill, have the disease, and then depending on the hospital, there's no person there to make the report. Usually it would be a nurse or an epidemiologist, which would make actual report the things, but sometimes this person is not there, or there is no person to do this job. It's the doctor. The medical doctor has to do the job, and while he is overwhelmed with other things, so no reporting happens. So what is better is in the case of Brazil, is the number of severe cases, which are hospitalizations. And hospitalizations have to be reported. So you use this time series of hospitalizations as a proxy of the number of cases. Okay? So you will try to use the new hospitalizations per week as modeling, being proportional to the number of cases. So that's the way that this is the same thing that is done for people by people that work with respiratory diseases like influenza. Influenza is also an extreme case where you don't know the number of people that have flu. Okay? So if you want to do models for flu, you will have to have some way of getting a proxy for the number of people that have influenza, and this is usually done with hospitalizations and sentinel hospitals also. Okay. Well, but then there's a further problem. So first, you have to attribute a time point, a day or a week to a case. So you say, I have a new case. Okay, what is the date attributed to that case? So typically, what you would like is to say the day the person got infected, that's a new case. Okay? So, which is difficult because you don't know you got infected. But, well, not so good, but still important, would be the day of the onset of symptoms. Okay? So the date associated to a case would be the date associated to the onset of symptoms of a person, okay? Which is very different from what you see when you get reports from governmental bodies saying today we had so many cases. That is usually what they are saying is the number of cases is the number of by the day the case was reported. It came into the data system. So this is not the date of the onset. And there's a delay between the onset of symptoms and that case being reported in the database. So, yeah. Mm-hmm. It's, yeah, that actually we thought that would be the case, but it is not, because the delay can be 3 or 4 weeks. Yeah. No, I understand. Yeah, because the delay, because that's the typical case when you have, for instance, you have an ongoing thing and then it's an epidemic. It's not just some cases here and there. And the delay is enormous. And it's not, I mean, it's also not constant. It's a distribution of delays. Yeah? And if you look at most of the epidemic curves by day of onset, they are like always decreasing at the end. It always seems that you have no cases, but it's just that you have not been reported. And you can do models also on a daily basis. It has a problem also. So maybe it's a good question. What's the difference of doing models on a daily basis or a weekly basis from the data? Why do you think in most cases in epidemiology you use the week, not the date? Well, do you aggregate more data? That's true, you aggregate have high, but in a case of epidemic like COVID and the 2020, every day had a lot of data already, okay? You could do it for daily basis, but what can happen else? What can go wrong? Hmm? Yeah, but I agree. It's completely heterogeneous, but you can do your reporting not for Brazil. I mean, I tried to convince you in the last class not to do models for whole Brazil, but for cities or metropolitan regions or mostly for a state. And then there's some homogeneity at this spatial scale. But one thing which happens also with the daily reporting, which seems ridiculous, but it's that on the weekends, you don't have so many reports because you don't have the personnel. So that's kind of, you know, and yeah, there are always this kind of thing. you can correct for that, actually. You can use statistical methods to correct for that. The people from demography have developed all of this kind of thing. Yeah. Yeah, that's true. And actually, but well, this you can try to, if you have a time series, you can try to model this, okay? But then there is also a thing, how do you know the date of onset? It's by declaration of the person. And do everybody actually remembers the exact day? So if you look at the time series per day, you have peaks at day 10, 20 at the end of the month. Why do we have? Because people say, okay, it was more or less about day 10. They don't remember if it was the 11th or the 12th. Okay, 10. So you have to correct this. Okay? So it's much easier to work with weeks because weeks are more homogeneous. Okay, what they are weeks, but you have long holidays. But anyhow, okay. So anyhow, incredibly, you have super delays in Brazilian data. I followed more closely the situation in Germany also, and their delay is 3 days. They still do corrections for that, but their delay is 3 days, and here it's 3 weeks. So you never know exactly the situation. So if you want to calculate your RT with some reasonable assumptions, what you have to do is to use a statistical method, which is called nowcasting. Nowcasting is, it's again with the word forecasting. It's not calculating the future, but calculating the present, because you know only the past. But you have some data about today, so you do a statistical model, and you predict how many cases, you make a statistical correction of how many cases you have today. When I say today, it's usually some days ago, okay? But anyhow, it's better than 3 weeks of. So what do you need is you need a database where you have each line of your database has to be a case, and you have to have the number of the date of onset of symptoms and the date of reporting when the person just typed the. If you have this date, then you can do a statistical model to make a kind of prediction of the number of cases today. And well, if you have the age, then you can also make this age structured. Okay, it'd be better. So if you are interested, you can go to this site here, which was created by people from our group, Rafael Lopes and Leonardo from Rio, which is it's a software which does nowcasting. You only need, you need data which have these 2 dates: date of typing, digitalization date, and date of onset of symptoms, and you rather have a long time series. Yeah. So let me go back to the. How do I get back there? Now I don't know how to get back. No, that's wrong. Okay, bad. Okay, so the kind of things that you get with nowcasting is this. You have a time series of the cases, and at a certain point, you do the corrections and you get this. But then you have error bars. Okay? You don't have absolute numbers. Okay? So, okay. So with this, you then, you can then estimate R of t. Then, okay. then you get things like that. Okay? It's highly oscillating. Okay, so that's fine, but mainly at the beginning of the epidemic. Because there have been a lot of people talking about using RT as a decision-making instrument. So if RT is smaller than 1, we can relax. If it's RT is bigger, we should take action, and so on and so on. But this is not really a good idea. First you have credibility intervals, or if you want, error bars in physics and language. Okay? So you have to take this into account. Okay? And sometimes they are quite big. So it's difficult to take decisions when you have a too high error estimate. But if you have a number of cases which is reasonably low, okay? After one big peak, you have a decreasing situation and so on. But you still can have local outbreaks. That local outbreak can generate an increase of RT, but which does not correspond to a general increase in the population, for instance, for a whole city, because the background is very low. So it's not an instrument for decision-making in all situations. It's a way to follow the situation of the epidemic, but people should avoid trying to use this as in situations where it is too sensible to small outbreaks. Because sometimes these outbreaks are localized. It's just a party, or was it just a certain industry, or people that were somewhere together, and it's not overall. So you need local indicators. It's much more complicated than just using R of T. Okay? Wow. And local indicators mean that you need at municipality level, or even at the neighborhood level, information about the spatial distribution of the cases, which is usually not, in the case of Brazil, it's not in the usual databases. Usual databases give you only municipalities. If you have a big city like São Paulo, that's not very useful from the spatial point of view. Okay, this second example of what we have done, I think overlaps a little bit what Renato probably told you on the online lecture. But just, let me be quick with this. We had a situation in the city of Manaus with when this new variant called Gamma variant, or P1 at the time, emerged, and we have a super high peak. And at that time, there was a lot of discussion because of the following situation. The situation was Manaus already had a very high incidence. There had been a super wave of infections months before, and people have even estimated the seroprevalence, and it was like 70 or 80% of the city. So you expected that you should be near herd immunity. You should not have a peak. But, well, you had a peak. So, well, you could have problems with your estimate of seroprevalence, a possibility. Or we could have something else. Something else would be waning immunity. Okay? So we built a model to study this, a compartmental model. And that's the kind of model that we have. You have the susceptibles, and then you have the two separate parts. One is the dynamics of the resident wild type COVID-19, and the second one is the variant, okay, which has different parameters. And there's a possibility that that people that had COVID-19 due to the wild type months before can be reinfected by the new variant. And then you take the data of the number of hospitalized people, and you take the data about the proportion of cases due to variant gamma with respect to the resident variant, and you fit the model. And so in this model, was also age structured, but only with 3 class ages. Okay? Just younger people up to 20 years old, then 20 to 60, and then over 60. Okay? And that's the kind of data that you need in this case. It's the epidemic curve and the proportion of the new variant in the situation. And what you get is actually you will fit when you fit a model, you have some parameters to fit. So one parameter that we left to fit was the prevalence at the beginning, at the introduction of the new variants. What was the prevalence of people that had already had the disease before, and then this was used in the fitting, and then there are parameters related to reinfection and to the force of infection, or to R0. So what we obtained is that the relative transmission rate, I mean, this is, you have the RT for the wild variant, and then you have the new variant, and how much is this new variant more effective? It's like 2.5, 2.6 times, and the prevalence of previous infection was actually what people had found before. This is curious, but you actually obtained that their result seems to be consistent. And here you could calculate, I didn't put it on the slide, but you could calculate the number of cases that would be reinfections. Okay? From the total number of cases, how many would be reinfections? And you can calculate this and you get like 28 or about 30. Okay? % should be reinfections. And curiously is that later on, this group from Mr. Sabino actually estimated the number of reinfections in the Manaus based on blood donor specimens. You go to blood donors and you test the blood, okay? And then you look if the person had been or not reinfected, and it's actually it's between 14 and 34. So that's what we found was kind of 30. So the picture is clear. You had a new variant in a population that had already a high prevalence, but the variant was very much infectious in the sense that it is 2.5 times more effective than the old variant, and it was able to reinfect people. Without reinfection, you could not explain the situation in Manaus, because if you had a prevalence of 78%, there would be no people to generate the peak as we had, but actually you have reinfection. Okay? This story about reinfection is curious because there there had been a lot of people talking about the possibility of reinfections at that time. But most of the time, yeah, Minister of Health of any country or whatever and so on, they will say, we only can say that we have a reinfection if you have a person that tested positive some time ago, let's see, more than 3 months ago, that went to a PCR, and then this person gets reinfected, has again a situation where the person is tested and gets a PCR. And so this is not so common, because you don't need to have PCRs all the time, okay? Most of the time, nowadays nobody, not if you have a critical case, yes, but if since 2021, with the, this rapid tests and so on, people don't get PCRs and so on. So there were no confirmed reinfections at that time because of this kind of definition of reinfection. But there have to be the reinfections. Otherwise, you cannot have the kind of epidemic that we have. So it's an epidemiological result, actually, coming from modeling epidemics, which then can be confirmed, obviously. Yeah. Okay. You got 2 PCRs? Yes. Oh, okay. You would be a count for the for the ministry. Yeah. Okay. You would count for that. Okay. So let me give a third example of things that you can do with modeling and with this situation of what kind of data you have. Like you have a certain a lot of uncertainties and so on. And this is a work that it's a little bit more theoretical that we did. It's you have 2-dose vaccines. Okay? So you have a certain efficacy of the vaccine of the first dose, and then you have to higher efficacy if you take the second one. Now, you could vaccinate people in most of the cases, but at least 3 weeks from the second dose should be at least 3 weeks after the first one, between 3 and 12. So what is better? Which is the best interval? Well, this will depend on several things. The first thing is the relative efficacy. Okay. If the first dose gives you a high immunity, then you better vaccinate as much people as you can, and then you give the second dose 12 weeks later, okay? Because you have already a lot of protection with the 1 dose, okay? At the limit, you could say, okay, I don't need a second. But if the first dose gives you only a small protection, then you better get the second dose earlier, right? So you could say, okay, when is the best time? And in such a way that in taking into account that you have a local, the distribution is limited. You have a limited number of doses, okay? If obviously you have infinite number, then I don't have any problem, okay? But you have a certain rate of doses being produced or being bought, okay? So should depend on this, and should depend on the efficacy, okay? Yeah. No, the point is they can give you, say it's better you take, let's say, 5 weeks, okay? But well, when you get vaccinated with the first dose, you have some immunity, okay? So, it depends on the vaccine. So the theoretical problem is if you're with one dose, you get a very low vaccination, very low immunity, then you better go for the first opportunity to get the second one, the second shot. Usually whatever, okay? It was like the minimum was 3 weeks. But if the efficacy of the first dose is high, over 70%, say, then it could be better to wait and give the second dose later, because you can get more people at the beginning. And so you are avoiding people getting sick and avoiding people dying from COVID. Okay? No, 2 doses. I'm talking about 2 doses. Yeah. Okay, okay. I will show you the results with the actual efficacies, which we took into account. Okay, so because this is also a method that can be done. I mean, for any, we have done this with the demographics of São Paulo and with the efficacies of CoronaVac, of Oxford AstraZeneca, and Pfizer-BioNTech, okay, that were taken from the literature. Okay? So this is an optimization problem where you want to have a objective function, which is to have a minimum of people of diseased people. And your parameters are your variable is the delay between the first and the second dose. And this should depend, obviously, on the production also. Okay? So what we have done, it's a model also which has 3 replicas. And then what you get is you will get a model, which is ordinary differential equations, but you have to have delay because you have a person getting vaccinated at a certain point. Then this person gets vaccinated a certain amount of time later. So you have a delay differential equation, actually. And so we use the demographics of São Paulo and actual values of the efficacies published by the companies and so on. And what you get is more or less this. You get that if the relative efficacies is a measure of the efficacy of the first dose. If it's obviously 0, then you better get the second dose as soon as possible, which is here, the bottom line. Okay. And you have a transition, but which is of this kind. More or less, the 3 vaccines behave in the same way. Okay? And if your production is low, then you can have you can wait for 12 weeks. It's the best interval in order to get a minimum number of people diseased. Okay? So this is also an illustration of what kind of job a model can do. We are not predicting anything. We are not trying to predict the number of cases, the peaks. Or in one case, for instance, for the gamma variant, what we did was calculate parameters that characterize the variant. And in this case, we are calculating delays between the first and second dose, which are optimal, so it's an optimization problem. So models are not meant all the time only to be predictive. They have other uses also, like this one. Okay? The final example I like to mention, it's will be quick. It's a counterfactual analysis, which is the following. You have a situation where you don't have any vaccination, 2020. And then you have the age distributions of cases. And there's a relation between, the relevant thing is people over 60. And then you have the people over, there's a relation between the number of cases of people over 60 and people that are below 60. And then you start vaccination with a class age of 80, but think about 60. And then this relation between the curve of cases of people that have that are over 60 and people that are under 60 becomes different because of vaccination. Because vaccination first, the first 7 months here in Brazil was only for people over 60. So you can estimate how many lives were saved. Because you can say, okay, I have still the incidence, I have the epidemic curve for people, say, of at the age of 40, and if there was a relation between this curve and the curve for people over 60 before the vaccination, maybe this continue to be the same, then, but now people over 60 are vaccinated, you have less cases. So you can calculate how many lives were actually saved or how many hospitalizations were avoided by this. It's not just a small proportion, so obviously you have to write a statistical Bayesian model and so on, but it turns out that this kind of analysis, which is a pure statistical analysis, tells you that with the 7 first months of vaccination in Brazil, which was population over 60, because obviously when you start a population to vaccinate people that are younger, you don't have any more the comparison curve. Okay, so you have to stop. Okay? So only for this period of time, we estimated that 165,000 individuals were not hospitalized due to COVID. Okay? But, and also that 58,000 lives were saved by vaccination. But then you can also do the counterfactual analysis, say, and if we started earlier, we could have started earlier if we had bought the vaccines earlier, okay? And if we started earlier by 3 months, I think, yeah. By 3 months, we could have avoided 104,000 hospitalizations and 47,000 deaths. Okay? So that's statistical analysis based on you have a epidemic curve with age structures for the period before the vaccination, and then when you start vaccinating, you see the effect, okay, on the age classes which are above 60, and then you can estimate how many people were saved or how many more people could have been saved if we started earlier. Okay, so I think that's all, but I'm going to be open for more questions or comments or whatever. Protests, disagreements. Yeah. Uh, 12 weeks, yes. That was indicated by the companies that fabricated that. It's a boundary of the company. Yeah, it's a boundary of the company. Okay, they had done some tests, and well, that was the boundary of the company. Oui. No, we stopped, our system stopped in February because there's no regular flow of data anymore. And the database has been modified and so on and so on. So our system. It is, but it used to be. Yeah, it is. It's called CWeb Grippy. And, but it used to be updated every Wednesday by Wednesday evening. And now it's irregular and so on. So we are not updating anymore. Yeah, and there are things like that, yeah. Yeah, sure. Okay, yeah, sure. Yeah, forgot it.
So earlier on, Flavio had a question about, you know, if we have the empirical results from the lab regarding the optimal interval between vaccines, why is this model kind of being used? So I just wanted to add an explanation to add to everything that, of course, Roberto already explained very well. So I think we need to understand problems at scale, right? So the empirical results that come from places like Butantan or pharmaceutical results in the lab are at the individual level. So these are individual immunity responses, right? So we're talking about models of immunity where you're looking at the dynamics of humoral responses or T-cell responses and so on. And so obviously you know very well at the individual level what the efficacy of a vaccine is in terms of protection. What is the top-up, the additional top-up between one dose to the next dose? And that allows you to understand at the individual what is the optimal interval between doses, right? What Roberto was talking about, and I'm again just adding to everything he already explained very well, was at the scale of the population, right? So now if you have a vaccine that protects you a fair amount, let's even say very low, like 20% in your first dose, at the population level, you are diminishing the probability that given a contact between an infectious individual and a vulnerable individual, that contact will actually incur into an infection, right? And also something very important about the COVID vaccines is that they were actually more useful to disease rather than infection, right? So these were vaccines designed mainly to prevent severity of disease, right? So it actually is still helpful because individuals that are partially vaccinated, even if they were to become infectious, they would shed less because they would be less symptomatic. And it actually still allows for a decrease in infectiousness. I think Joshua, and I think Roberto as well, explained beta, so that kind of probability of infection that has a lot of traits pertaining to the pathogen and of course to the host. And so it plays with that probability, right? That optimal interval. So that's just something I wanted to say because it actually will relate to the problem of scales that I will focus on the final lecture. But it really depends on what question you are asking and at what scale you are evaluating the solution.
Sure. Yeah, let me give you the mic. I think the camera will become completely crazy when I come here.
First, thank you, both answered, and I agree. You got only the big scale in phase 4 in a clinical trial, and you don't change the time between 2 doses. So I agree, and thank you. Something that I want to ask you is Butantan did a controlled experiment in Serrana. It's a little city. And did you?
No data.
Sorry?
No data.
No data. So no question anymore.
No data. Never published.
No data?
Never published.
Wow. No questions.
And the director of the program quit.
Yeah, I know.
And I mean, what's kind of invited to quit. And yeah, they never published the results of coronavac in the city. Never published. Here's. More questions? Why did they not publish? More questions? Let me just make an observation. So no question. I will talk for 5 minutes. Okay. So the photo will be outside? Yeah. Okay. Okay, so let's go for the photo. Okay. Okay, thank you. Yeah.